space and time in classical mechanics. The purpose of mechanics is to describe how bodies change their position in space with time. I should load my conscience with grave sins against the sacred spirit of lucidity were I to formulate the aims of mechanics in this way, without serious reflection and detailed explanations. Let us proceed to disclose these sins. It is not clear what is to be understood here by position and space. I stand at the window of a railway carriage which is traveling uniformly and drop a stone on the embankment without throwing it. Then, disregarding the influence of the air resistance, I see the stone descend in a straight line. A pedestrian who observes the misdeed from the footpath notices that the stone falls to earth in a parabolic curve. I now ask, do the positions traversed by the stone lie in reality on a straight line or on a parabola? Moreover, what is meant here by motion in space? From the considerations of the previous section, the answer is self-evident. In the first place, we entirely shun the vague word space, of which we must honestly acknowledge we cannot form the slightest conception, and we replace it by motion relative to a practically rigid body of reference. The positions relative to the body of reference, railway carriage or embankment, have already been defined in detail in the preceding section. If instead of body of reference we insert system of coordinates, which is a useful idea for mathematical description, we are in a position to say the stone traverses a straight line relative to a system of coordinates rigidly attached to the carriage, but relative to a system of coordinates rigidly attached to the ground, the embankment, it describes a parabola. With the aid of this example, it is clearly seen that there is no such thing as an independently existing trajectory, but only a trajectory relative to a particular body of reference. Note, trajectory is a curve along which the body moves. End of note. In order to have a complete description of the motion, we must specify how the body alters its position with time. For every point on the trajectory, it must be stated at what time the body is situated there. These data must be supplemented by such a definition of time that, in virtue of this definition, these time values can be regarded essentially as magnitudes, results of measurements capable of observation. If we take our stand on the ground of classical mechanics, we can satisfy this requirement for our illustration in the following manner. We imagine two clocks. of identical construction. The man at the railway carriage window is holding one of them, and the man on the footpath the other. Each of the observers determines the position on his own reference body occupied by the stone at each tick of the clock he is holding in his hand. In this connection, we have not taken account of the inaccuracy involved by the finiteness of the velocity of propagation of light. With this and with the second difficulty prevailing here, we shall have to deal in detail later. Part 4. The Galilean system of coordinates. As is well known, the fundamental law of the mechanics of Galilei Newton, which is known as the law of inertia, can be stated thus. A body removed sufficiently far from other bodies continues in a state of rest or of uniform motion in a straight line. This law not only says something about the motion of the bodies, but it also indicates the reference bodies or systems of coordinates permissible in mechanics, which can be used in mechanical description. The visible stars are bodies for which the law of inertia certainly holds to a high degree of approximation. Now, if we use a system of coordinates which is rigidly attached to the Earth, then, relative to the system, every fixed star describes a circle of immense radius in the course of an astronomical day, a result which is opposed to the statement of the law of inertia. So that if we adhere to this law, we must refer these motions only to system of coordinates relative to which the fixed stars do not move in a circle. A system of coordinates of which the state of motion is such that the law of inertia holds relative to it is called a Galilean system of coordinates. The laws of the mechanics of Galilei Newton can be regarded as valid only for a Galilean system of coordinates.